All right. The torsion pendulum is actually way easier to do than the physical pendulum, believe it or not, even though the torsion pendulum is a very unusual kind of case. It looks kind of weird. Basically, the way that it works is that um, normally like pendulums, right, they swing side to side. This one actually doesn't really like swing side to side. It rotates side to side. So what happens is there's a disc and there's an elastic rod. You can displace the disc a little bit, and then what happens is it rotates, and you can find a video of it online. Basically, it's like a little disc and it rotates between two, it oscillates between two, I guess like theta points, right? This consists of a rotatable cylinder having rotational inertia I connected to an elastic rod at its axis. The elastic rod twists so that the torque provided by the rod depends on the angle the cylinder is rotated with this equation right here, negative beta theta. I love the sound of that equation, beta theta, where beta is a positive constant that depends on the physical properties of the rod. Beta is like the rotational spring constant. I think it's actually called like the torsion constant is what it is. It basically is like the spring constant, like how well something takes like twisting and stuff like that. Okay. To solve this, I'm again going to use the net torque is equal to I alpha, but this time I'm actually straight up given the torque equation. So this is actually a little bit easier. Okay. And set that equal to I alpha. Well, alpha again is the second derivative of theta, and I can divide I on both sides. So when I do that, I end up getting negative beta over I theta equals d squared theta over dt squared. And guess what? That's the simple harmonic motion differential equation right there. Okay. My negative omega squared is negative beta over I. Okay. So now what I got to do is I just pull negative omega squared equals negative beta over I. Okay. Drop the negatives on both sides. I get omega squared equals beta over I. Ooh, I. Okay. And then root both sides to get omega equals root beta over I. Okay. Pretty straightforward. Okay. Okay. And then what I can do is I will now set this equal to 2 pi over t. Okay. And what I can do then is figure out the period. So I'm going to flip both sides like I always do. T over 2 pi equals root I over beta. Okay. And then I will multiply 2 pi on both sides to get t equals 2 pi root I over beta. Okay. Okay. That's the equation. That's the derivation for period. That's actually all you really need to know for this right here is that you need to know how to get that period equation. Okay. So that's an equation for that. I don't think this one is on the formula sheet. If memory serves me correctly, I don't think it's on the formula sheet if I'm not mistaken. I could be wrong. I don't have a formula sheet with me right now, so I can't check, but I don't think I know the physical pendulum is. It's called like T sub phys, but I don't think that the torsion pendulum is on the formula sheet. Okay, so just this might be something that you might have to be able to derive or on the test. Okay. All right, and it's also important to note that this, by the way, is very similar. I was just about to wrap up, but I'm going to point this out too. This is very similar to the spring mass oscillator. Okay, because if you look at spring mass, the spring mass case, it's T equals 2 pi root m over k. But then if you look at the torsion pendulum, okay, then you have t equals 2 pi root I over beta. Okay. Now, these are very similar because m and I are both measures of inertia. Okay, or like mass, right? And then K and beta are measures of elasticity. So very, very similar to each other. Okay. All right, that is the torsion pendulum. Okay, after that's the last of simple harmonic motion stuff, because now we move on to gravitation. Okay, all right. Take care. Watch out and take care.